In this video, we're going to discuss how to use the binomial theorem to calculate the probability of a repeated event. Okay, so to use the binomial theorem to calculate the probability, first of all, you need to be repeating an event, say over and over and over. There's no set number of times, but any repeated event. But what's really important is that you have an event that is defined as either pass or fail. Okay? And that pass or fail idea, they have to be complementary. So the probability of success plus the probability of failure has to equal 1. Okay? And whatever you decide is a success and whatever you decide is a failure, well, it's kind of left up to the user. But let's just talk about repeating the experiment of flipping a coin. So in this case, the probability of heads plus the probability of tails is equal to 1. Those are complementary events. So yes, those would be defined as a valid means of doing the binomial theorem for calculating the probability. And so what happens is, it's easy. If you're going to flip a coin 8 times and calculate the probability of getting 8 heads. So that's super straightforward. In fact, I think we did that earlier in this section. You would just do the probability of heads times the probability of heads, etc. It's because that would be heads and heads and heads and heads. We're going to look at it in a slightly different manner this time. We're going to think of it like this. Basically, the probability of getting 8 heads, there's only one way that can happen. It can happen as literally getting 8 heads in a row, and that is the only way for it to happen. One outcome that this effectively is described. Okay, and so what happens is there are 8 trials, and you're getting 8 heads. So 8C8 is one possible way to get 8 heads from 8 trials. If we look at it for a second, though, if we think about the probability of getting 7 heads and 1 tail, there are 8 choose 7 ways for that to happen. In other words, there are 8 trials, and we're going to choose how to get 7 heads. 8C7 is 8, by the way. So think about it this way. You can actually map out these 8 outcomes pretty easily. You could take a minute, but hopefully you'll get the idea of why there are 8 total outcomes here. Basically, you could get 7 heads and then a tail. You could get 6 heads, a tails, and then another heads. You could get 5 heads, a tails, and 2 more heads. You're going to work this tails backwards, basically. 4 heads, a tails, and then 3 more heads. So we're listing all of the different ways to achieve 7 heads and 1 tails. This is one of those opportunities. This is one of those times when I wish I was able to voice over and kind of fast forward through my work. Hopefully that's eventually coming down the line. But so now we got to the point where we are 1 tails and then 7 consecutive. So any of these 8 outcomes, any single one of these 8 outcomes fulfills that 7 heads and 1 tails. So you can get this, or that, or. So you have lots of different ways to satisfy 7 heads and 1 tail. All right, so what? Well, what happens is this whole thing is modeled. Remember back here? This was 1/2 to the 8th power because it was a probability of getting probability of getting heads repeated 8 times. Well, that's essentially what's happening here, too. In each of these line items, 1, 2, 3, 4, 5, 6, 7, 8, the probability of getting 7 heads and then a tail is 1/2 to the 8th power. 1/2 to the 8th, 1/2 to the 8th, etc. on down the line. What happens here is we've got 8 combinations of 1/2 to the 8th power. And this can actually be modeled with a term from a binomial expansion. This would be 8c7 times the probability of heads to the 7th power times the probability of tails to the 1st power. Relate that back up to here. This would have been 8c8 times the probability of getting heads to the 8th power times the probability of getting tails. How many tails did you get? 0. All right, now let's look at this little trend. The probability of getting 6 heads and 2 tails would be 8c6 times the probability of getting heads to the, you guessed it, 6th power times the probability of getting tails to the 2nd power, because you'd be getting those 2 tails. So I hope you can see that this is the first couple of terms of a binomial expansion. And so what you can do is you can model these probabilities based on that binomial expansion. Okay? Now, let's actually look at a few examples and actually compute the numeric values of these things. So let's do it. Instead of 8 times, let's use 12 times. So we're going to flip a coin 12 times consecutive. And we're going to compute the probability of getting 6 heads and 6 tails. So here's how we're going to do that. We're going to do 12 trials, choose 6. Honestly, it doesn't matter whether you use the first or the last, but just use the first number usually. So it's 12c6 times the probability of getting heads, in other words, 1/2 to the 6th power. So that's the probability of getting heads. Then the probability of getting tails to the also 6th power. So these exponents should add up to 12. And this is, again, you can choose either of these exponents to be that number down there. And what happens is you jam this whole thing into your calculator, you should get 0.451 something, something, something. And that is the probability of getting exactly 6 heads and 6 tails, right around 50%. Pretty likely. Probability of getting 12 heads and 0 tails. Again, if you just think about it as 12 straight heads, you would get 1/2 to the 12th power, because it's the probability of getting 12 heads 12 times in a row. If we do it using a binomial expansion, it would be 12c12. Remember that notation? This means the same thing as 12c12, which is 1, by the way. And then you get the probability of getting heads to the 12th power, which is the same as we have here. And the probability of getting tails to the 0th power, which, by the way, is 1. So this whole expression simplifies to the same as this. Okay. By the way, numerically, very unlikely, 0.0002. So this would be 0.02%. So that's pretty unlikely to get 12 heads and no tails. 3 heads, 9 tails would be 12c3 times 1/2 to the 3rd power. That's the probability of heads. 1/2 the probability of tails to the 9th power. Again, 0.05 something, something, something. Probability of 9 heads and 3 tails is identical to this. If you remember back in the combinations unit, 12c3 was equivalent to 12c9. So that was a little fact that was nice to pick up on. So what's going to happen is, since 12c3 is equivalent to 12c9, this term is going to equal that term. And now heads is just as equally likely as tails, so now it's going to be the probability of heads to the 9th power and tails to the 3rd power, which, again, numerically, these are equivalent. So it is equally likely to get 9 heads and 3 tails as it is to get 3 heads and 9 tails. So that is how you use the binomial expansion to calculate the probability of a repeated complementary experiment.